let's have a look at some valid row operations. We'll have a look at the system 2, 1, 0, 2, 3, 4. Okay, so this is an augmented matrix that's basically A with our right-hand side vector B, if we're talking about the set of simultaneous linear equations expressed in matrix form, AX equals B. So this is what we're looking at here. Now, the valid row operations we can do, we can multiply or divide a whole row by a scalar. So for example here, what we could do is we could say, well, row 1, or you can use capital or lowercase letter, row 1 star for new row 1 equals row 1 divided by 2. Because dividing by 2 here would make the element in the pivot position, this pivot position here, equal to 1, which is what we like to see. Now if we do row 1 star equals row 1 divided by row 2, our new matrix becomes 1, 1/2, 0, 2, and then we always need to remember to also apply this row operation to the right-hand side value, which is 3 on 2 now, and 4. Okay, so that's our first valid row operation, multiplying or dividing a whole row by a scalar. Another row operation that we can perform is swapping entire rows. Now, because I'm showing you the row operations here, our aim isn't actually to end up with the identity matrix, it's more to just explore what we can actually do. So swapping rows, we could say, well, our new row 1 equals the old row 2, and our new row 2 equals the old row 1. When we do this, we're just swapping the entire row. So we get 0, 2, and then 4 on the right-hand side, 1, 1/2, and 3 on 2 on that right-hand side there. We can also put this little squiggle that means that these matrices are equivalent. So that's the second valid row operation, is swapping rows. Okay, now the third row operation that we're going to talk about is add or subtract a scalar multiple of one row from another. So this can be one of the trickiest row operations to perform. But what you can do is you can do your scalar multiple first if you like, and then do your addition or subtraction. Your scalar multiple also can be just 1, which means you'll just be adding or subtracting a row. So let's work back with this matrix here. And we have, let's say that row 2, I'll keep with what I've been doing before with the lowercase letters. Row 2 star, our new row 2, equals row 2, and we'll take away a quarter of row 1. So let's see what happens if we do this. So our scalar multiple, it can be a fraction if we like, it can be a whole number, it can be whatever we want. But now that we do that, our row 1 doesn't change, so our matrix is equivalent to 0, 2, 4 for that first row. And the second row, we had 1, 1/2, and then 3 on 2. We were subtracting a quarter times row 1. So 1 subtract a quarter times 0. Then we had 1/2. So 1/2 subtract a quarter times 2. And then 3 on 2 subtract a quarter times 4. So you can write it out like this if you are a little bit confused or not quite understanding what's going on. Just write it out more fully. Now, because we did write it out fully, this line down the middle does get really funky. So we'll try not to do that too often. Let's evaluate what happens here. So that's equivalent to 0 to 4. 1 take away 0 is 1. A half take away a half is 0. 3 on 2 take away 1 is a half. Okay. So we've sort of headed towards the identity matrix and then again away again. But because this video isn't about Gaussian elimination, it is just about row operations. We won't continue with this here, but we will talk in the next video about how to actually perform Gaussian elimination. So hopefully you understand our row operations a little bit better. As a reminder, what we can do is we can multiply or divide a whole row by a scalar. We can swap 2 rows, or we could add or subtract a scalar multiple of one row from another row. They're the 3 valid row operations that we use when we're performing Gaussian elimination, and doing any of those operations won't actually change the system we're working with.